All right, folks, we're back for part two here, where we actually get into the process of cluster analysis, which is pretty cool, and hopefully you find it fun. So we're going to break this down into two steps. So the first step is what's called hierarchical clustering, and this is what gives you essentially what looks like a kind of like a upside down family tree, I guess, right? It's called a dendrogram. It's a clustering that basically starts by first pairing together the most similar observations with each other, and then starts pairing those groups over and over iteratively with each other until you essentially are down to two groups and then one group. So it basically goes from everyone is their own cluster by themselves to everyone's in one group, and you get all the steps in between. And then your process is basically to decide which of those solutions, all the way from the 333 individual clusters, right? Because we have 333 people, to the one single cluster is the best. So this is called hierarchical clustering, and it's very easily implemented in R, which is great. So the command here is hclust for hierarchical clustering. And what you have to do, there's one little tricky element here. So you have to be aware of a couple things. You have to be aware of your distance metric. And we talked about this in the lecture. There are different kinds of distance. There's like city block distance, Euclidean distance, Sherbyshev distance. We're going to use Euclidean distance, and these are all just sort of slightly different mathematical sort of geometric calculations of distance between 2 points or a set of points in a plane. So Euclidean is a pretty standard one. And then you have to be aware of what what clustering method you're using too. So we're using here Ward's method, which is again one that we explained in the lecture, and also a method that's described in your chapter on cluster analysis. But there are other methods of hierarchical clustering. Ward's is not the only one, but it's probably the most common. So the command here, what we do, we actually nest a command inside of a command. So the part I've highlighted right here, we have to create what's called a distance or dissimilarity matrix. So that is basically a set of distances between all the points using the specified metric of distance that we want. And so that's what dist is. So first, the software is going to calculate a matrix of distances based on the core data set, which remember is just those three variables: importance, hours spent on homework, and engagement, just those three. And all three of those are numeric. So those are the rules. You can't have binary variables, at least in this kind of clustering. You can't have factors. You can't have character variables. You can't have logicals. All that stuff's got to be gone. So you want to trim it down just to the numeric variables. And it's going to calculate the distance, and then it's going to calculate the clusters. And it's amazing how fast this actually goes. That was it. So in that amount of time, that the advantage of cluster analysis is that these algorithms are very fast. And so, it's not like a statistical model where you might find yourself sitting here for a few minutes, wondering if it's actually going to run. So you get a little message. If you just type hclust, it gives you a summary. You get a little bit of a message of what you're looking at. So, so the clustering method here was Ward's method, ward.d2. The distance measure used was the Euclidean, and there were 333 objects, which is equivalent to the number of observations in our data set. So stored in the memory in this object is the full cluster analysis. And if you just do plot hclusts, you actually get the full dendrogram, which is pretty cool. So this is the whole thing, the whole dendrogram of going from 333 observations pairing up the most similar observations all the way to up here where we have a group of only 2 and they're combined. You can also make this a little bit bigger. You can pop this out in a new window. So I will show you that because this has a lot of complexity to it, and R will resize everything. So these numbers, which are kind of overwritten on each other, I believe these are row numbers. So these are all individual row numbers here for people that are being combined. So there are 333 of these at the bottom. And you can see, for example, all these pairings, these are the most similar pairings of observations down at the bottom. And then eventually you start to see pretty quickly these bigger groups forming. And so, for example, if I draw a line going across here at a height of 20, that's a 2-group solution right there. So those are the 2 groups, and they're basically split right here, right down the middle. This is the 3-group solution, 1, 2, 3. This is the 4-group solution, 1, 2, 3, 4. This is the 5-group solution, 1, 2, 3, 4, 5. Go a little bit further down, 1, 2, 3, 4, 5, 6. Okay, most of the variability, most of the sort of difference is explained by those last 6 groups. Those last 6 groups seem to make the biggest difference. A lot of these combinations down here are very similar, and that's why their height is so small. It's a lot of similar observations being combined. But when you start making these big jumps, it means that the groups you're combining are quite different. So our job is to figure out what is the optimal solution. And there are lots of ways of doing this, but I prefer a statistical approach if possible. So I'm going to close this. And this is where the NB-clust package is really, really fancy and helpful. So what NB-clust does, it has a set of, I think, 15 or 20 different fit statistics that it uses to test on each solution, going from the 333 clusters all the way to the 1 cluster. And it tells you what the best solutions are according to the different fit statistics. It's kind of like a meta-analysis for your cluster analysis. It basically like runs, because there's the thing in cluster analysis, there's so much differing advice as to like which statistic to use. You know, in Stata, we use this statistic called the Kolinsky-Harabaj pseudo F statistic, which is pretty good, but there's also a number of other criteria that you can use. So I think this NB-clust package does a nice job of kind of summarizing all the evidence and giving you kind of a best case scenario to look at. So we're going to run that. The command, by the way, is NB-clust, which is the name of the package. You need to give it data, and you need to give it a method. And in this case, we're doing Ward's clustering, which is hierarchical. And you get some pretty cool stuff. So I'm going to skip first to the output here, the actual text output. And it gives you a lot of information here that's pretty useful. So if you go up to the top, it has a description of the 2 graphs that you see. So there's graphical ways of finding the best solution based on changes in fit statistics, but then it also tests all of these indices. So there are, let's see, 5, 7, 11, 16, 17, 18, 19. So there's 23 different indices, fit indices that were used. And it tests and says how many fit indices agreed with 2 clusters, 3, 4. And so these are the possibilities. So we had 2 cluster, 3, 4, 6, 9, 13, 14, and 15. And there were 5 indices that proposed the 2 cluster solution as the best. So there's some evidence there that the 2 cluster solution is our best option. But there was also a pretty close one here. The 6 cluster was pretty close too. It also had 5 indices. Now, according to the rule, the way that they calculate this, if there's a tie between 2 packages or between 2 cluster solutions, this package is going to recommend the simpler solution, which isn't a bad idea. That's kind of good in general. If you have a simpler solution and a more complex solution that look equally plausible, it's probably better to take the simpler solution. There's just less that can go wrong. But here, based on this, the 2 cluster solution is probably the best, although 6 looks pretty good as well. And then we can also look at this graphically. So these are a little bit harder to interpret. So these are what are called Hubert statistic values. So what you're looking for basically are where these things start to turn the corner, either start to go more vertical than horizontal, or more horizontal than vertical. So you can see here, there's a little bit of a turn here between 2 and 4, and there's a little bit of a turn here. And then this is the second difference of that statistic. So basically what you're looking for are these big jumps. So there was a pretty big jump here right around 5. So if we went off of the Hubert statistic, we would probably say that the 5 or 6 cluster is the best. Probably the 6 cluster is the highest here if we use the Hubert statistic. And this is just a visual representation. And then this is the same thing. This is called the D-index. This is another fit statistics. You don't need to know necessarily what it is. It's just measuring measure of fit for the clusters. And what you're looking for are spikes in the D-index, and there's a spike at 6. Although 2, again, was equally good and recommended because it was basically the same. All right. So that kind of gives you a little bit of a guess here. If you're thinking, wow, that's, there's a lot of subjectivity there, you're absolutely right. And that is the nature of cluster analysis. Cluster analysis is highly subjective, which I think is super cool. It makes it a powerful tool for trying to understand things that aren't necessarily easily understood by a more straightforward model. But it also sometimes makes it harder to wrap your head around what's going on. Another cool feature that you can do here, you can actually highlight what the solution looks like in the dendrogram. So what does the 5 cluster solution look like in the dendrogram? You just run the plot function, and then right after it, you run this rectangular hclust command. And then k equals 5, that's just the number of clusters you want to see. So here are your 5 groups. So this is the first group. This is the second, the third, the fourth, and the 5th, like that. And you can change it. So if you want to see the k equals 2 cluster, you just change that to 2. And there's your second cluster. So basically everyone here is in the first group. Everyone here is in the second. If you wanted to see the 100, actually that's probably too many for this picture. The 8 cluster solution, it'll draw that for you. So there are your 8 different groups. So kind of a cool thing also, just sort of visualize exactly what's going on. So that is hierarchical clustering. And so the best approach, and I think I talked about this in the lecture, is to typically combine hierarchical with what's called k-means. And you hope that you find similar results. Because if hierarchical and k-means give you consistent results, it means you probably have something that's pretty durable. K-means uses a very different approach, right? It uses these sort of random starting points and measuring distances, and sort of iteratively works around and around until it optimizes in a solution. And in k-means, you have to give it a starting point. You have to say, I think there are 2 clusters or 3 or 4, and it will test those things. Oh, I should say too, we tested all the way from 2 to 15 solutions up here for hierarchical when we did the nbclust command, and we're going to do the same thing below here for k-means. All right, so so for k-means, oh sorry, we're just going to do 1 to 9 instead of we're not going to go all the way to 15. I forgot about that. So for k-means, this is where tidy models is really helpful, because it can sort of collate and combine a lot of information and allow you to use it very easily. So you first call the tidy models package, which I think we've already loaded in, and then you're going to call this object k-clusts. The first thing you do is, and I would just use this exact code and just change, literally, all you need to do is change core. Core is your data set that has the data in it. And 1 to 9 is the number of profiles that you want to test. everything else, if you change core, right, core here, core there, and you change it there, everything else will run automatically using tidy models. It'll create all the different forms of the data set, which is great. So that stores everything in there. And then we can unpack this a little bit. So we can get a clusters data set and assignments and a clusterings. So we'll just look at these really quickly. So the clusters data set, we pop that open. So this is the this is a data set that basically shows you the solution, so the cluster solution and the fit statistics and the variables that were included and the size of each cluster. So here, for example, the first thing we did was a 1 cluster solution. So there were 333 people in it. Then a 2 cluster solution, here are the 2, then a 3 cluster, then a 4 cluster. And these are actually the cluster means. So you could put these in a bar graph, for example, and you could compare the means across the groups. Some people might be high importance, low engagement, so on and so forth. So that's kind of a cool thing you can do with the clusters data. And then assignments. This just breaks down for each solution who is in which cluster. So it covers for all the solutions which observation is in which cluster. So it's actually a pretty big data set. And then the clusterings is a little bit smaller. So this is just a summary of the different solutions from 1 to 9. So here's the 1 cluster, the 2, the 3, 4, 5, 6, 7, 8, 9. Here are the fit statistics, total sum of squares, total within, between, so on and so forth. So that's just some cool stuff that you get. You don't have to do anything with it, but it's there, and it's kind of helpful. So then I recommend throwing these solutions into a scatter matrix to try to get a sense of what the groupings look like. So to do this, you have to pick 2 of your variables. You can only do this with 2. Now we have 3, but I just picked math importance and math engagement. So I just put those in here. And that's really the only thing you need to change. Everything else should run. You just put in the name of your variables. And you get this really cool little plot. So each one of these is a solution. So notice 1 cluster in the little 1 up here. This is the 1 cluster solution. So everyone's in the same group. This is the 2 cluster solution. So here we have this group that emerges here in the lower left. Then there's 3, 1, 2, 3, and 4, 5, 6, 7, 8, and 9. So it allows you to sort of visually inspect the quality of the solution and see the extent to which stuff makes sense. So the way this is laid out, the vertical axis is math engagement. The horizontal axis is math importance. So to use this example here, to use the 2 cluster solution, which was one of our candidates, people in the red group in cluster 1, these are people who are high importance, high engagement. So that might be one way that we would describe the characteristics of the first cluster. People in the second group, the sort of gold group down here, they are lower engagement, lower importance. So that might be one way to split them out. Cluster 6 was also a possibility, if I'm not mistaken, either maybe cluster 5 or 6. And actually, yeah, cluster 6 looks pretty clean. So here, cluster 1, these are the highest engagement, highest importance folks. The gold are the lowest. And then you have these really interesting combinations of people in the middle. So as you add complexity, now sometimes it gets really hard to separate. For example, if you look down here at the 10 cluster solution, the blue group and the green group are essentially overlapping. And over here at the 7 cluster solution, that doesn't look good either because the teal group and the blue group and the gold group, they're all kind of mixed in. And so that it's harder to sell a solution like that because the groups are not terribly distinct. And that's really what you're hoping for in a cluster solution. If you want to make this even clearer, you can add X's, and you actually don't need to change any of this code. It'll just, as long as you have a plot called P1, it'll add an X to denote the groups. So right, so here's the 1 group solution, 2 group, 3, 4, 5, 6, 7, 8, 9. And you can see, for example, in the 5 cluster solution, the gold and green sort of overlap. And the X is at the, it's at the centroid or the center of the cluster. So if they overlap, again, that's a sign that the solution is probably not that solid. So it's a cool way to visualize all the different, this is kind of like X marks the spot, which is kind of cool. And then the last thing you can do, our good friend NB clust also works with k-means. So not only can we sort of inspect each solution visually, we can do the same thing with NB clust and get all those fit statistics and get a recommendation statistically as to whether or not the solutions that worked best for the hierarchical clustering also work well for the k-means clustering. And here, according to the majority rule, 5 is the best number of clusters because it had 6 fit statistics that recommended 5. 2 was right up there though, right? It had 5 statistics that preferred it, so that's interesting. And again, we get those same sort of information here. So we have a spike in our plot here at, I guess this is at 5, but we also had a spike somewhere else. And then we have a spike here at 5 as well. So it appears that the solution here would be 5, although if we look back up at the wards didn't love 5, right? So there were none that agreed with 5. So some say 5, some say 6, and the only agreement we really get is 2, right? 2 was pretty consistently a strong performer. So if I had to make an argument, I would probably say we're looking at 2 clusters here. Although 5 or 6 does look pretty tempting as well. And so that's part of your argument. As you're trying to describe these clusters, you're trying to say, you have to think about theory, of course. You have to think about what you know about how these things would relate to one another. And you have to think a little bit about what the fit statistics are telling you as well. So there's definitely more objectivity or subjectivity in this than in other kinds of statistics. And keep in mind, this is an exploratory method as opposed to a lot of statistical modeling, which we would consider to be confirmatory, where you have pretty set hypotheses heading in. Cluster analysis, similar to exploratory factor analysis, which we'll learn next week, is an approach that you sort of go in with fewer guesses as to what you're going to find, and you sort of let the data kind of guide what you can see. I think that's probably a good stopping point. The last step, of course, which I'm not going to demonstrate here, would be to validate this cluster solution. So that would be to go to use the data from the clusters that I mentioned up above, and to do something like an ANOVA or something like that to compare based on SES, which was my external variable. So in my 2 cluster solution, do students in those clusters differ according to SES? Maybe according to theory they would, I'm not sure. But that's the sort of last step, is validating that cluster solution. So there you go. That is just a little dose of cluster analysis in R. Hope you found that fun, and we'll talk to you soon.